Now we reached to this equation in the last video. If you look at this equation, we see that there is a difference between the normal component. E1 is the normal component above the surface and E2 is the normal component below the surface. So there is a difference between the normal component of the electric field below and above the surface. We can say that the normal components of electric field are discontinuous, and they are discontinuous by an amount sigma divided by epsilon naught. So once we introduce a surface in between 2 points, then the electric field across this surface become discontinuous, and the discontinuity is by a factor which is sigma divided by epsilon naught. Now to check the we already checked the discontinuity of normal component of electric field. Now we have to check the discontinuity of parallel component of electric field. So here I will plot the same figure again. We have the same surface. This is the same surface, and I will plot only the front face of this box, because the parallel component is along this way. So we need only the front face. So the front face will look like this one. This is the front face. Now here point 1 is here and point 2 is here. So E2 direction will be, E2 parallel direction will be this one, and E1 parallel direction will be this one. Now I will calculate the electric field along this closed path. I will start from here. I will move to this point, then I will go to this point, then I will move to this point, and then I will come back to this point again. So for that we say that the closed line integral of E dot dl is 0, which we already know. Now here if I look at here, then we have how many paths? 4 paths. One is this path. If I move like this, then the direction of dl is this one. If I move from here to here, then the direction of dl will be this one. If I move from here to here, then the direction of dl will be this one. If I move from here to here, then the direction of dl will be this one. So here the direction of dl is this one, and here the direction of dl is this one, while the electric field direction is this one. So they are perpendicular to each other because the angle is 90. So it means that E1 parallel dot dl is equal to 0 because this is a dot product. So cos 90 is 0. And similarly E2 parallel dot dl will also be equal to 0 because the angle is theta is 90 degree. Now we left only 2 paths now. One is this one and the other one is this one. Now E1 along this path, E2 parallel and dl, they are parallel to each other. So we have dl cos 0 plus along this path we have E1 parallel, and we have dl cos 180 because the dl direction is this one while electric field direction is this one, is equal to 0. This implies that E2 parallel into L minus E1 parallel into L is equal to 0. We can say that E2 parallel minus E1 parallel is equal to 0. I can say that E1 parallel is equal to E2 parallel. Since E1 is above the surface and E2 is below the surface, so it means that E1 parallel, is E above and E2 is E below. Now we will calculate E above minus E below. E above minus E below. Now this equation tells us that the parallel component of electric field is continuous even if we introduce the surface with charge density sigma there. The parallel component will continuous while the normal component will be discontinuous, and the discontinuity is by a factor sigma divided by epsilon naught. So we can say that E above minus E below. E above is E1, perpendicular component of E1 above. I can say that, I can write it here again. This is the surface, okay? And here we have 2 points. One is above and one is below the surface. So above we have E1 above. E1 has 2 components, one is parallel, one is perpendicular component. Similarly, E2 has 2 components, one is parallel and the other one is perpendicular, E2 perpendicular. Now below, upward, like the unit vector which is perpendicular to the surface, I call it N, and the unit vector which is parallel to the surface, I call it P unit vector, PK. Now E1 perpendicular, its direction is upward, so we have, if I wrote it in vector form, then I will put this vector here. Now plus E1 above, E1 parallel above times its direction is parallel to the surface, minus E2 perpendicular, this one its direction is upward, plus E2 parallel, its direction is parallel to the surface. So this is the electric field above the surface and this is the electric field below the surface. Above the surface we have 2 components, one is E1 parallel perpendicular and one is E1 parallel. Parallel component is along the surface, so I put this unit vector P here, and the perpendicular component is perpendicular to the surface and the unit vector along the perpendicular direction is N, so I put N here. Similarly, below the surface we have 2 components, one is E2 parallel and one is E2 perpendicular. E2 parallel is along P direction and E2 perpendicular is along normal direction. So here I can write E1 normal or perpendicular component plus minus, I will put this one first, E2 normal or perpendicular component plus E1 parallel component minus E2 parallel component. We know that E1 parallel is equal to E2 parallel in either case, whether there is a surface or not. So if this is the case, then this cancel with this one. So we left with E1 normal minus E2 normal. And we know that you can write it as E1 normal minus E2 normal into N unit vector. And we know from this equation that E1 normal minus E2 normal is sigma divided by epsilon naught. So here I will put sigma divided by epsilon naught N. This is E above minus E below is equal to sigma divided by epsilon naught n. So there is a discontinuity in electric field above and below the surface once we introduce the surface between 2 points. This is called electrostatic boundary condition for electric field. Now we check the discontinuity of potential. Now we will check the discontinuity of potential. For that, I consider again the same surface. One is 0.1 and the other one is 0.2. 0.1, 2. Now I call it point A and B. And this is the distance D, which is much smaller. We know that the difference in potential VB minus VA is equal to integral from A to B E dot dl. But we know that since D is much smaller, so if D is much smaller, then this integral E dot dl will be equal to 0. So it means that VB minus VA will be equal to 0. Or we can say that VA is equal to VB. Now VA is above the surface. This is the surface here. And B is below the surface. So we can get the potential above is equal to potential below the surface. So there is no discontinuity in potential once we introduce the surface there. The potential will remain the same. Now E above minus E below is equal to sigma divided by epsilon naught n into n from the previous equation, this one. But we know that E is equal to negative gradient of the potential minus del into V. So E above will be equal to minus negative gradient of V above, and E below will be equal to minus negative gradient of V below. Now using these two equations, here we get minus del V above plus del V below is equal to sigma divided by epsilon naught into n. I can say that del V above minus del V below will be equal to minus sigma divided by epsilon naught into n. Taking dot product of n on both sides, del V above dot n minus del V below dot n is equal to minus sigma divided by epsilon naught n dot n. Now these are unit vectors, so their dot product will be equal to 1. So we have del V above dot n minus del V below dot n is equal to minus sigma divided by epsilon naught. I can write it as del V above dot n minus del V below dot n is equal to minus sigma divided by epsilon naught. This is basically equal to partial V over partial n, and V is above, minus partial V below over partial n is equal to minus sigma divided by epsilon. So the gradient of the potential below and above, they are discontinuous, but the potential is itself continuous there. So we have 4 important results. The first one is parallel component of electric field is are continuous with or without surface. Like the parallel component of electric field will be continuous whether there is a surface or not. The second conclusion is normal, or we can say that perpendicular, components of electric field are continuous when no surface charge is there. Surface is there. By surface I mean surface with charge. And the third conclusion is normal or perpendicular components of E are discontinuous when surface is there. Surface is in between the two points. Like in this case, E1 parallel is equal to E2 parallel, whether the surface or not. Here if there is no surface, then E1 perpendicular will be equal to E2 perpendicular. But if we introduce a surface with surface charge density sigma, then E1 pair normal minus E2 normal will be equal to sigma divided by epsilon naught. Like the normal component of electric field will be are discontinuous, and discontinuity factor is sigma divided by epsilon naught. The third conclusion is the potential is a scalar quantity. So we have only one number, it's a number. So there are no components of potential like E1 parallel or E1 perpendicular. So it's a scalar quantity, so we don't resolve it into components. So the potential will be as a whole. The potential is continuous. Like potential above will be equal to potential below. While the most important is the gradient or the derivative of normal derivative of potential above and below the surface are discontinuous, and the discontinuity factor is sigma divided by epsilon. So we have 3, 4 and 5 conclusion from boundary condition of electrostatics. The first one is like the parallel component of electric fields are continuous whether we introduce a surface or not, while the normal component of electric field, they are continuous if there is no surface between the 2 points, and the normal component of electric fields are discontinuous when there is a surface charge inside 2 points, and the discontinuity factor is given by this. Now the potential is a scalar, so we don't need to resolve it into components like V parallel or V perpendicular, because V is a scalar, so it's a number, it's not a vector. We can resolve vectors only, not scalars. So whenever we are talking about V, so it means this is a number. So the potential is continuous in either case, whether we have a surface or not. So potential above the point surface will be equal to potential below the surface. But the derivative of potential, the normal derivative of potential below and above the surface, they are discontinuous, and the discontinuity is by this factor. So this is all about electrostatic boundary condition. In the next video, we will move to the topic of work done to move a charge from one point to another point. Thank you.